Arvind will tell us about fast exact algorithms.
Thank you, Shubhangi, Madhu and Amir for inviting me to this wonderful workshop. I am now inspired to learn more about invariant theory and understand the null cone problem. But this is really about upper bounds and not lower bounds. Completely down to earth stuff, really. So there are two problems. Yeah, this is joint work with Abranil, Rajit and Partha. Rajit and Partha are from Chennai Math Institute. Abranil is a student at the Institute of Mathematical Sciences. They are PhD students. Partha was my PhD student. Rajit is Partha's PhD student, so they're like family. Okay, so these two problems are what I'm going to be talking about. KMLD is given an arithmetic circuit C, computing a polynomial in this multivariate polynomial ring. The problem is to decide whether it has a non-zero degree k multilinear monomial. And KMLC is like the counting version of it. You want to add up all the coefficients of the degree k multilinear monomials in C. Okay, so the background is work of Kutis and Janus Kutis and Ryan Williams around between 2009 and 2012, I should say. A bunch of papers where they actually defined these problems, and the idea is to attack combinatorial problems that arise in fixed parameter complexity by posing them as algebraic problems and using powerful arithmetic complexity ideas to solve these problems. Okay. So you would notice that K here is not part of the input, it's outside as part of the problem definition in both cases. That's because K is a fixed parameter. So as you all probably know, this is the field of parameterized complexity. Just a quick recap. So usually, along with the input instance, when you want to bound the size of a solution, either lower or upper bound, it would come as part of the input. And you would ask for a solution to the instance I, which has whatever weight of size k or weight at most k, etc. So instead of that, you take k out from the problem definition. So I is the input, and you treat k as fixed parameter. By which what you mean is that you think of k as something much smaller than the input size, and you don't care if your running time is going to be enormous in k, but you want it to be a very, very small growing polynomial function of the input size alone. So what is acceptable as efficient algorithm is a running time of the kind fk times the size of the input to a small constant c. C should be independent of k. C should be independent of k to avoid some obvious brute force solutions where you're looking for a solution of size k. So this is what is called fixed parameter tractable. FPT for short. So the class of parameterized problems that have such algorithms, you put in the class FPT, and the goal is to design algorithms with as small a c as possible and as small an fk as possible. Of course, you are reconciled to the fact that f of k is going to be exponential, because typically you are looking at NP-complete problems and you know that it's sanity check tells you that it can't be polynomial. But there's also an accompanying hardness theory, which is an additional sanity check, and that's a notion of hardness. I won't tell you much about it because I want to get onto those two problems. So there is this complexity class with a weird name called W1. Okay, a complete problem for this class is the k-click problem. Is a complete problem for this class. So you don't expect, for various reasons, to get an algorithm that is of running time n to the small o of k for the k-click problem. And another complete problem is, for example, for 3 CNF SAT, weight exactly equal to k, Hamming weight k solution. So this is another complete problem. So where do arithmetic circuits come in when we are dealing with combinatorial problems? So let me give you a quick example, which will be one of the running themes of my talk as well. This is the k-path problem. And given a graph G, it's a directed, and you ask, does there exist a simple k-path? So let me quickly pose it as a k multilinear detection problem for you. So this problem is known to be in FPT. It has an FPT algorithm, an algorithm of running time 2 to the order k times n square or something like that. Let me pose it as a k-MLD problem. The idea is, so let's say A is the adjacency matrix of the graph G. Let's define a new matrix B whose ijth entry is Aij into Xi. And so let's consider the matrix B to the power k minus 1. And let me multiply it with a column vector x1 to xn. So xi's are these indeterminates, one for every vertex. And here let me multiply it by the all ones transpose. So what is this? This is actually the sum of all monomials of degree k, because this is going to contribute k minus 1, and the last one is going to pick up k, degree k, such that I1, I2, Ik is a walk in G. Multiplying xi by aij ensures that the adjacent pairs of variables are actually form an edge, but there could be repetition of vertices. And multilinearity is precisely what is going to check for simplicity of the path. So if you take this polynomial and you solve the k-MLD problem for it efficiently, then you get an algorithm for the k-path problem. So, and Ryan Williams, in one of the papers that I mentioned up there, and independently Kotis, gave an O star 2 power k algorithm for this problem, formulated as a k-MLD problem. In fact, they solved the problem only for f equals z, only the characteristic 0 case. And to get the run, in fact, they solve it only for the case of monotone circuits. For monotone circuits, when and therefore f is z, they get an algorithm whose running time is O star suppressing n to the constant. Running time is essentially 2 power k. This is for directed graphs. For undirected graphs, of course, Björklund made this huge breakthrough in 2010 For undirected graphs, he has this algorithm of running time O star for the general Hamilton path problem. I shouldn't write O star, forget it. 1.657 to the n, which also gives a fixed parameter algorithm, something like 1.66 to the power k O star. This is for undirected graphs. For directed graphs, this remains the best running time so far. But for arbitrary fields, the problem was open. And additionally, so the KMLC problem is easily seen to be a hard problem. So you can't expect an FPT algorithm for this. I'll explain that in a moment. So, but what should I say now? Yeah, okay. So for the KMLD problem. So for the general KMLD problem, where you allow negative coefficients in, so Brand and Holger Dell et al. In stock 18, Dell et al. They gave an O star 4.32 to the K algorithm for the KMLD problem. And the KMLC problem, you can't expect a running time like this. This I'll explain quickly why in a moment. But what Ryan Williams did was to show that if the field is of characteristic 2, then you have an O star n to the k by 2 algorithm for computing the sum of all coefficients of degree k multilinear monomials.
So what is known about the complexity of these problems in terms of NP hardness? And
They're all NP hard.
All are NP.
All are NP hard.
They're Sharpie.
The counting version is Sharpie. So so consider the following problem. Same setting, G is an undirected graph now. Consider sum of all, consider the quadratic form consisting of the edge monomials, degree 2, raised to the power k. What is the multilinear degree 2k part of it? It's a k matching. And if you want to solve the KMLC problem for this, it's counting the number of k matchings, and that's known to be sharp W1. Complete. Number of k matchings. So you can say Ryan Williams' result shows that you can compute the parity of the number of k matchings, for example, and much more, because for any arbitrary circuit with integer coefficients, you can add up the coefficients modulo 2. So, okay.
But excuse me. So that counting problem, so in principle you can reduce it to computing just one coefficient.
One?
Yes. So if you multiply by symmetric polynomial n minus k and look for the product of the guys there.
But the degrees will go up, no? So here the fact that these are small degree monomials plays an important role.
So in principle there are like riser kind of formulas. Are they like reason for 2 to the power k?
Sorry, in principle?
There are risers.
I'm going to use riser, yeah.
Okay.
So maybe you're already anticipating what I'm going to do. So let me write down here or here.
Are there graph theoretic problems where you actually need this KMLD for non-monotonic thing with non-negative arbitrary coefficients, etc.?
That's a good question. Let me proceed with the talk and okay. First is for KMLD over any field, we get an O star 4.32 to the power k, same running time as Dell et al. And additionally poly space. Running time is exponential in k, but it takes only polynomial space, whereas their algorithm needs 2 power k space. And for
the notation O star that you use,
it suppresses polynomials,
I see, okay, in
polynomial factors in n and k. Input size basically.
So should K
KML for KMLC we get an O star n to the k by 2 plus an order log k, and for all fields.
This is the one which was sharp W1 hard.
That's right. So you can't really hope to get something like this. I mean, get k off the top really, but we can save a factor of 2 in the exponent. And the reason I'm giving this talk is because we use non-commutative polynomials to do this. So the techniques are something that go back to an earlier paper from around 2010 that I wrote with Pushkar, Joglikar, and Srikanth. And that's the reason why our algorithms are really simple and intuitive. For example, the Dell et al. Paper uses exterior algebras and all fairly sophisticated math tools. And what we do is simply transform the problem, do a kind of transfer from the commutative setting to the non-commutative setting. And in the non-commutative setting, monomials look like words. And then you can do something like automata theory there. And that helps us in a big way. So,
deterministic.
sorry?
The algorithms, are they
No. So this would be like solving PIT. I mean, if it,
okay, so
so for example, I could just multiply this with, I mean, it would essentially be like solving PIT.
But how come just their method is algebraic in US, but the same 4.32 comes? What?
Very good question.
Why?
Because both methods use what is called color coding. It's a technique of, perfect construction of perfect hash families. These parameters come from the right choice of perfect hash families. The size of explicit hash families that hash subsets of size k in a domain of size n into a range of size k or something slightly larger.
If it's like sort, but 4.32 to the k should still be okay with PIT and deterministic. So what's the problem?
No, k, but k was k could be n, no? Oh, that's what you mean.
Right. If k is as large as n, this is exponential. So your algorithms, it could be determined.
But it's not. In the end, we do use PIT, and I don't believe it can be made deterministic either.
See,
Okay, sorry.
your algorithms are black box in that they're just applying the polynomial. They don't look at the arithmetic circuit that's computing the polynomial.
That's largely true. Largely true. Let's get into the actual proofs. So let me quickly recall the non-commutative setup. I have a field f, and instead of x1 to xn, I'll have non-commuting variables. And to make a distinction, I'll use angular brackets. So y is y1 to yn. The non-commutative partners of x1 to xn. And let me also recall the Hadamard product of two polynomials. But that I will need the definition in general. But let me first recall in the non-commutative setting. So let's say f and g are two polynomials. The Hadamard product is basically what Leonid had defined in his talk. It's just the sum, something like the inner product along with the monomials tagged on. F sub m is the coefficient of the monomial m in the polynomial f. G sub m is the coefficient of the monomial m in the polynomial g. And the Hadamard product of f and g is simply coefficient-wise product, which gives you a new polynomial. A similar definition, in fact, I will require in the commutative setting as well. Let me quickly summarize the work with Pushkar and Srikanth from 2010. What we could show are the following results. Suppose f is given by an algebraic branching program, non-commutative. G is given by an algebraic branching program. Then let's say this is of size S1, this is of size S2. Then the Hadamard product is given by an algebraic branching program of size order S1 into S2. And I like to think of this result as simply telling us that regular intersection regular is regular. And it's basically the product construction done carefully looking at coefficients. Coefficients matter. So in that sense, it's a bit different from taking the intersection of automata, but it's pretty much like that. Second is, suppose f is given by an ABP of size S1, G is given by a circuit of size S2, then their Hadamard product is given by a circuit of size order S1 cube times S2. And this is essentially like saying CFL intersection regular is CFL. And essentially the proof also works the same way. But something very interesting happens here, which allows us to do things in a black box setting, as Russell was saying. What we could do is we could take, suppose you had a circuit C for G, only available as a black box. We could compute the Hadamard product of F with G by feeding for the variables the matrices that correspond to the algebraic branching program F. In the sense that you take the algebraic branching program, make a matrix with as many rows and columns as the number of nodes, square matrix, and in a particular entry, what you will put is the coefficient of the variable xi in it. So mxi would be mxi, the lkth entry. What you could do is you can take the coefficient of the variable xi in the linear form, labeling the edge L comma k, and also multiply it with the variable xi. So for each variable myi, because we are working in the non-commuting variables, myi. So we have one matrix for each variable, and if you evaluate the circuit on this bunch of matrices, and you look at the start comma end entry of the matrix that comes out, that will contain the polynomial which is the Hadamard product of f and g. So you could evaluate it at any particular point by plugging in the values of the variable yi's that you want. Okay, so why do we?
So this is, I mean, this can be made truly black box because you could just learn the matrices. You could just reconstruct the matrices for the ABPs and then, I mean, even if you had given black box
F also, you mean?
F and G, you could do that.
In the algorithmic setting, those things are, yeah.
I mean, but the original setting is commutative.
Yeah, the original setting is commutative.
Oh, sorry.
So it's not fully black box.
Okay.
Excuse me.
I'm running out of time, so I should speed up and at least explain one of the results.
The size of the circuit didn't figure into the runtime at all, right?
The size of the circuit
For results 1 and 2.
here, no? So
These results.
if I want to evaluate which
These
one?
results there.
Well, there are O stars.
But the size of the circuit, O star was also in polynomial.
The input size. O star conceals polynomial in input size. Okay. So let's
So you want some function.
so what should I do to
So you want some function f whose support is exactly the multilinear.
so I should take the elementary symmetric polynomial.
Yeah.
So let's call that S and K. S and K is the degree K elementary symmetric polynomial. The problem is that, so what I would like to do is the following. I have the elementary symmetric polynomial. So, and let's look at the polynomial that I wrote down for the K path problem. This is the polynomial that adds up all the walks of length K. We are in the commutative setting, and what I'd like to do really is to take the Hadamard, the commutative Hadamard product of S and K with this polynomial. Because if I do that, then what I'll pull out is precisely all the multilinear terms, and I'll be done. Only thing is I don't have an efficient algorithm for the commutative Hadamard product. For example, if you take x1, x2, xn and take its Hadamard product with product I going from 1 to n, summation aij xj, j going from 1 to n, then this is the permanent of A multiplied by x1 to xn. Of course, here things are of much larger degree and not of degree k, but I want to transform things into the non-commutative setting so that taking the Hadamard product is not going to be an issue for me. So what should I do? How do I ensure that I don't, if I simply take, so if I take SNK for example, I have an algebraic branching program where the indices are ordered like I will have, I will really be adding up things of this kind where I1 less than I2 less than Ik. If I freeze this ordering and I take the Hadamard product, I might miss many terms because here in the walks things could be coming in different orders. I don't want to miss any of the terms. So what should I do? So that I can transfer this to the non-commutative setting, take the Hadamard product and be able to recover the commutative Hadamard product. So the answer is the simple answer. If you don't want to miss any terms, what we need to do is to take all possible permutations of the variables. So let's define that polynomial as Snk star. Snk star is summation. Now we switch to the non-commuting variables yi1 to yik, where i1, i2, ik is a subset of 1 to n of size k distinct indices. So if I have a small description for Snk star, that's wishful thinking because I cannot have one for it. If I could have a small circuit description for Snk star, then in this commutative polynomial, I simply replace all the xi's by yi's, make it non-commutative. But here, because I'm considering all possible orderings, I'll be able to trap the multilinear monomials if they exist in any case.
Will you end up getting even extra terms that you don't want?
No, because Snk star has only multilinear monomials, no other terms. And this has walks of length k, and you're looking for ones with distinct variables.
But isn't this just the exterior product? Like you said, the other paper used exterior product.
Yes.
But isn't this just the explicit form of it?
Sorry?
Like, isn't this just the explicit, like the exterior product written explicit?
Yeah, maybe it is. I don't know that much math. So let's, but I'm only thinking of it as non-commuting variables appearing in all possible orders. So my elementary symmetric polynomial, the non-commutative version, simply considers all permutations of it. Okay. So I want to quickly describe this result.
Are you going to have a separate set of variables for each degree position?
One non-commuting variable corresponding to each variable there.
I was thinking about the question you asked. So are you going to introduce a distinct set of variables for every degree position? Like have cases?
No. I'm not doing that. Okay, so this is Snk star. So let me make this general statement that if I want the commutative Hadamard product of f and g, and I want the coefficient of a monomial in the commutative Hadamard product of f and g, what will it, so here suppose I replace this by f star, and this is the non-commutative Hadamard product. The coefficient of any monomial m prime, which when permuted gives me m, what will it look like? What I'll get additionally is an m factorial term, where that m factorial is the monomial m is x1 to the e1, etc., xn to the en, m factorial is e1 factorial, etc., en factorial. So this is the extra multiplicative term I'll get. Because I'm considering all orderings, these permutations don't change the monomial, and exactly this much overcounting happens for each such monomial. Okay, so if I define the scaled Hadamard product as essentially the coefficient of m in the scaled Hadamard product is m factorial times fm times gm, then what I can say is that I have an algorithm. If I have a small circuit or algebraic branching program for f star or g, I need something for both of them, then I can compute the scaled Hadamard product essentially. And for multilinear terms, it doesn't matter because this m factorial is not an issue for multilinear terms because all the EIs are either 0 or 1. So m factorial is going to be 1. Okay, so with this kind of sketch, let me describe a couple of these results for you. First one is, it's easy to compute the Hadamard product of any polynomial with a pi sigma circuit. The scaled Hadamard product. So if f is given by a circuit and g is a pi sigma formula, then I can easily compute the scaled Hadamard product. By easily, what I mean is, okay, so let's say this is the pi gate is of Fanon k, then this can be computed in time O star 2 to the k. And the proof for this is simply applying Rice's theorem. So let's call this G. What I want to do is treat f as non-commutative in the order that it's given and replace G by G star. And then I know that if I can find a small description for G star, then I can apply one of the results there. I have a circuit for f, G star, if I have an ABP, then I'm done. Okay? And I have an ABP I have in fact a sigma pi sigma circuit for G star where the sigma gate is of size 2 power k. What is the matrix that I'll consider? L1, L2, Lk, L1, L2, Lk, L1, L2, Lk, and compute the permanent of this. The permanent of this actually gives me G star because it's going to multiply. I have replaced in the Li's, the Xi's have been replaced by the Yi's. So it's going to give me all the permutations that I need. And so G star will actually have a 2 power k Fanon sigma gate on top, a pi gate of Fanon k followed by the linear form. So once we have this, it's very easy to get the 4.32 4.32 to the k algorithm. So let's say f is the circuit and I need to do something to search for the multilinear monomials. What I'll do is I'll take the Fk as perfect hash family. Let's call it f. So these are all functions. I'm overloading the letter f. Let's call it h for hash function from n to k, such that for all s contained in 1 to n, cardinality s is equal to k, there exists h in f, such that h is injective on s. And it's known that cardinality f is nearly what is given by the probabilistic method, e power k times k power log k or something. This is the best possible perfect hash family, that maybe times n. So take the Fk as a perfect hash family. So given a hash function f, I can write down what do I do? So given a hash function h, so this is x1, x2, xn, this is 1 to k. Take the pullback of every point here, that gives me a linear form there. Take the product of those linear forms, the k linear forms that I'll get. So let's call them L1, L2, Lk. Each Li is basically the pullback of a point there where the points here are replaced by variables. And you add up over all the e power k times k to the log k many terms. So this is somehow this sigma pi sigma depicts the entire FKS family. And what do I need to do? I want to take the commutative Hadamard product of this with my polynomial f. That's all I need to do. So I will riserize this to get a non-commutative polynomial the way I described here. What will that incur me? Another sigma gate with a 2 power k Fanon. So when I riserize this, I'll get a sigma 1, sigma 2, sigma k here, where, and I shouldn't write that, but whatever. I'm not actually explicitly running over all k factorial permutations. I'll do what Riser does in his most clever way, and you'll get this 2 power k Fanon sigma gate. And now I'll replace the variables by the non-commuting variables and apply one of the older theorems to take the Hadamard product. And what it gives me is a 2e power k O star time algorithm. Now to get to 4.32, what we'll do is, in order to beat the e power k, we will relax the range here and go up to 1.3 times k. That seems to be the best choice of parameters. Then it's easier to perfectly hash subsets of size k, and then e gets replaced by 2.46. And in these monomials here, I'll also add a plus z. So the pullback plus z. In some sense, it's like I'm only interested in degree k monomials, but now because the range is 1.3k, I can get up to degree 1.3k monomials. So z is to kind of push away the things that I don't want, and I'll multiply f by z to the power 0.3k. So that will force only the degree k multilinear part to come out, and this gets replaced by 2 to the power 1.3k times 2.46 to the power k. The riser becomes 2 to the power 1.3k, and this number is 4.32. In the last 1 minute, let me just end with a nice comment about, I could have phrased this entire thing in terms of the rectangular permanent, which is a very interesting object of study. So basically, suppose A is a k by n matrix. Define the permanent of, or the rectangular permanent of A to be the sum over all injections from 1 to k to 1 to n. So there are k rows and n columns, and the injections pick out k columns, and you will compute the permanent of, how should I write? A sigma, let's simply say. Sigma selects those k columns. So what do you guess is the complexity of the rectangular permanent? It turns out that if the entries come from a commutative ring, then there is a 2 power k times poly n algorithm. If Aij come from a commutative ring. And the proof is very easy. It's again an application of the same thing. So here you take Snk, and here you take the product of the sums of the standard thing, no, that product of summation aij xj, product of the row sums. And you can riserize the product of the row sums with a 2 power k, and that's what you pay for here. But it turns out that you can't do this in the non-commutative setting. If you allow the entries to be matrices of size poly n, then the problem is W1 hard, sharp W1 hard. If entries are n by n, let's say. I'll stop here. I won't describe this algorithm.
Questions?
So would you answer my question? Which I
What is the question? Oh yeah, okay. So
What was the question?
the question was, why do you even bother about circuits that are not monotone? I'll give you an answer to that.
Huh?
I'm giving an answer to that. See the polynomial Snk star, so it's from the perspective of trying to convert everything into non-commutative, apply automata theory to solve the problem. So if you look at the polynomial Snk star, it's basically like the non-commutative rectangular permanent. You take the matrix with non-commuting variables y1 to yn in each row, then the permanent, rectangular permanent of that is basically Snk star. You'll see all the degree k monomials in all permutations. And that is hard, as I just told you. Okay? But an interesting question is there a polynomial which is weakly equivalent to Snk star? That is easy. Because for multilinear monomial detection, a weakly equivalent polynomial is good enough. Here what we got was a weakly equivalent polynomial. See, notice this, this polynomial. Oh, I erased that. Sorry. So what I did was, I took this perfect hash family. For every hash function, I wrote down a product of linear forms corresponding to the pre-images, added up over all the hash functions. That is a polynomial that is weakly equivalent, because every monomial that I get there will be multilinear degree k. Only thing is, some monomials will be counted very often. In fact, Nizan has proved that you can't get a polynomial like this where everything is completely balanced. Okay, so there will be unevenness, but it's still monotone. So it still doesn't answer your question. But what we can do is, we have a acute ABP, non-commutative ABP of size O star 2 power k, which has negative coefficients and which is weakly equivalent to Snk star. It has negative coefficients, unfortunately. So now what we can do is, so if you take the Hadamard product of this weakly equivalent polynomial to Snk star with the graph polynomial that I just showed you, which has also gone away, the 1 transpose b to the k minus 1 x1 to xn. If you take the Hadamard product with that, that will give me an ABP that is going to be non-zero if and only if there is a path of length k in it. So I have a non-commutative ABP of size 2 power k, or O star 2 power k, which is non-zero if and only if there is a multilinear monomial of degree k. I can check this in randomized 2 power k time. So that gives me a randomized 2 power k algorithm. So I don't mind getting a weakly equivalent ABP of size 1.66, like for example, if you want to emulate Bjorklund, which has negative coefficients, which is weakly equivalent to Snk star. Then I'll beat the 2 power k bound, which seems to be the point beyond. For directed paths, it's not clear how to go beyond that.
Thank you.
One more quick question. Yeah.
So actually, for that quantity which you were looking at, some of those multilinear, Okay, there is a Riser-like formula for that, and actually it
Everything
shows,
is riser here. It's
yeah. But okay, I was a while ago. It shows, by the way, in what you're doing. This is how you compute the number of matchings of given size, say in bipartite graph. And I think that formula is optimal. Yeah, it was in my paper with
so counting the number of K matchings is sharp W1 hard. So clearly there can't be any easy formula.
No, it's not easy. It's like what you said. And it's, I think it's essentially the optimality is, Riser's formula is optimal. Riser formula, it's Warring rank of polynomial x1, x2, xn, which is exactly that 2 to the power n minus 1. So it cannot do better. So, and essentially optimality in those things, it's you compute Warring rank of those things which you take the product. But anyways.
Can I add one more comment? There's nothing else after this. Just the last word on since he mentioned Warring rank, there is a beautiful paper by somebody called H. Lee from 2016, which shows that the Warring rank of the elementary symmetric polynomial Snk is n choose the downward, whatever you call it, the sigma n choose r going from 0 to k by 2. And if you take the Warring decomposition, you don't need to worry about making it non-commutative, because you just replace the xi's by yi's, it just becomes, it's the same thing. There's nothing to permute then. So that is basically what gives, and that is one way of getting this bound here.
Yeah. That was it.
Okay, I'll stop.